to the second of the lectures on the discovery of the Higgs. So let's start by the thing that probably all want to talk about, the Nobel Prize. So, in case. Yeah, so on Tuesday, as many predicted, the Higgs was given to Peter Higgs and Francois and Blair here for their contributions to development of the Higgs mechanism. And also,
were they involved more people?
Yes, right. So you can, that's a good question. So basically, Higgs, at the same time as Blair and another guy named Brout, had developed basically simultaneously this idea. So I think that Blair and Brout's paper, they perhaps, yes, they had written it, maybe submitted it a month before, but this was, of course, prior to the age of everything being on the internet, so they had no idea that they were working on the same thing, and they independently came to the same conclusion. There was another set of 3 people whose names I'm not going to get correct, who were also working on this and sort of more fully developed it, but that was about a year later. And the interesting thing, so that's development of the Higgs mechanism. That's the idea that there can be a field somewhere in space that has this non-zero value, even when there's nothing around. So that was the idea. But actually, they were applying it not to particle masses in the electroweak theory, which is where the Higgs mechanism we now know applies. They were trying to use it to explain how protons and neutrons and things like that acquire mass. So they were actually applying it in the totally wrong system, but the idea was so novel and it was so fundamental that that's why they got the Nobel Prize. There were a lot of articles this week about, can you really, in this era of large-scale science, can you really give a prize to just 1 or 2 people? And particularly, this Nobel Prize would never have been awarded had the Atlas and CMS experiments not amassed enough evidence to observe it, because it's just a theory until you can, it's just a hypothesis until you can show that there's some physical mechanism for it to exist. But, I think we're, at least in the experimental community, most people are, I feel it, are pretty happy about the fact that this is if we see it as recognition for the particle physics itself, for the standard model, and for this global collaboration, even if we're not explicitly given the award. It would have been kind of nice, I think, if the award had gone to CERN or something general, like also the Atlas and CMS collaborations, because this work really, because then everybody would have ownership of it. I mean, there's countries all over the world who've contributed to it. And so, for example, on the biology prize went to a guy at Berkeley and a few other institutions, and I'm from Berkeley, so of course we get emails, so, a Berkeley professor won the Nobel Prize. But if you did this for the Higgs, or for the Higgs, then you give it to the Atlas and CMS collaboration, and then I feel like everybody can feel ownership, because everyone essentially has someone in their state, in their institution, who has contributed to this, and your tax dollars have gone to this. So you've contributed, and so that's why it would have been nice. But at any rate, I feel like that's the idea that we most of us take, the opinion of most of us take for this thing. And so it was very exciting. It was a lot of fun. These are people, the webcast, they webcast the announcement at CERN, so this is a bunch of people. I think they have champagne all ready for it. Peter Higgs, he's like really, really, really shy about this. He is really, really uncomfortable with people calling it his boson and his mechanism. I saw him give a talk in July at the European Physical Society meeting, so both of them got an award then as well, and he basically spent the entire talk explaining how it really wasn't him who did all this work. I mean, yeah, he contributed to it, but it really wasn't him. So he's so self-effacing that he went on holiday without a cell phone, without any means of communication, and was like, I'm not going to be available on the day of the Nobel Prize announcement, because he just didn't want to be in the middle of all that. So that's part of the reason why it took so long to get them to announce it. But anyway, this is very exciting, and I think it's nice for us on these large experiments to just kind of have that validation that it's seen as a globally useful exercise. Oh, okay, but there are two things that I wanted to cover with this, which, so there's been a lot of coverage over the past week, of course, about it, and one analogy that came up that is kind of neat, that I just want to share with you. It explains kind of how audacious the idea of the Higgs field is. So we talked about last week the fact that there's a Higgs field everywhere all the time, no matter what's around, right? And that's a crazy thing to wrap your head around. It's an insane idea. And so the analog to this is, I first read it in this Frank Wilczek article that I actually posted on the blog. But imagine that that there's a planet somewhere, and it's a water-based planet, all water, and it's got sentient fish, fish who are developed enough to have started understanding physics and physical laws. And one fish sits there, is trying to understand some random things about her environment, right? She's like trying to understand how they swim. And she just starts thinking, and she thinks, well, what if we're actually in this thing called water, right? Water's all around us. And that's just, she just posits this idea that there's this thing called water, when they have no way of knowing what not water is, right? And not water doesn't exist in their world. So that's just the kind of idea, that's the analogy which I kind of liked, and that it's everywhere, it's ubiquitous, it's something that we take for granted. And yeah, so that's the idea of things. But any specific questions about the Nobel announcement?
Yes, I wanted to know, if you win the Nobel Prize, will everybody here be able to get your autograph?
Yeah, next year maybe. No. So a lot of times they do give one for the experiment one year or theory the next, or vice versa, for a lot of things. But they have this unwritten rule that you don't give the science prizes to more than 3 people. So that's why it was cut off at Higgs and Blair. So there was some thought that maybe they would break this rule and give it to CERN as a entity, but they didn't. So, and I do think this will get a lot harder, because now people, when you write a paper about an idea, you can post it online and everybody can read it in just a few minutes. And so individual ideas don't develop in isolation anymore. Yeah.
So what happens if we repeat these experiments and they fail?
To find the Higgs.
Right?
To repeat the experiment to find the Higgs.
Yeah.
So as we'll learn over the course of this lecture, we've seen thousands of Higgses at this point. We only know that there's Higgses once we've established enough statistical evidence that there are Higgses. And that's a really important part about what we do. And so, yeah, next week we'll start talking actually about how we start amassing that evidence. So so basically we won't fail, because we won't. We can, at the very end of the course, we'll talk about where we go next from this point. And it's hard to convince people to build $10 billion accelerators. So they're not going to let us just repeat it by building another machine to do the exact same thing. All right. So, was there anything more about the Higgs? No. All right. So, it's just the scheduled lectures. So today we're going to talk about our accelerators and how we create new particles out of what I call very thin air. And you'll see how thin it is. So I just want to start with a brief review of last week so everybody's on the same page. So last week we learned that the Standard Model describes fundamental particles and forces, so indivisible particles and forces. There are 3 forces that make up the Standard Model. This is the strong force, which binds quarks together. The electromagnetic force, which we're all very familiar for interacting between electric charges, and the weak nuclear force, which is responsible for things like nuclear decay. And then these forces act on 6 quarks, which the lightest of the quarks make up the protons and neutrons, and 6 leptons. Electron being the most familiar of those. And then we also talked about the Higgs field and how it exists everywhere, all the time. And a particle's mass is determined by how strongly it interacts with the field. So the Higgs field interacts, is the only particle, I think, in the standard model that interacts with, okay, it doesn't, sorry. It interacts with almost all the other particles. It does not interact with photons or the gluons because they don't have any mass, but interacts with everything else. And yeah, it kind of is the anchor to the standard model. And then the Higgs boson itself is the physical manifestation of that field. All right, so I do want to clear up one thing that was confusing last week, and as I was thinking about it after the lecture, I realized that I had forgotten very basic freshman level physics when explaining this to you. So I put up this plot, which is confusing, which shows the electromagnetic field strength on the x-axis and the energy of that configuration on the y-axis. And what you see is that for the electromagnetic field, it has its lowest energy, or zero energy, at zero value of electric field strength, which makes sense. When there's nothing around, you have no field. And then I showed you this one, and it was the Higgs field strength on the x-axis and the energy. And what you saw was that that the values went negative at non-zero field strength, which means that this is the most natural configuration, the lowest energy state. The confusion was that we discussed what is negative energy. And that is a question that you can't actually ask. There is no such thing as absolute negative energy until you start talking about general relativity, which I have not studied, so I can't comment on that. But at any rate, this scale is arbitrary. All that we measure is changes in energy. So we can only measure changes in energy. So this means that we know that this energy state is higher than this energy state, but there's no meaning to being negative. This is only negative with respect to this point. Is that, forget who asked the question, but that's more clear? Yes?
Yeah, I asked it. So with that clarification, that it's relative, so maybe you answered this, I'm not sure, it went over my head. But so I would change the question to, well, what is it relative to? And then secondly, relative to that, what is a definition of energy that's applicable from which you could form some concept of what negative is?
Okay, so I can tell you one way of talking about negative energy. So if I define this table to be energy equals zero, so what goes into this energy right now is just its mass energy and its gravitational potential energy. So if I define this table as zero energy, then when I put the pointer down there, it has negative energy because it has this much less gravitational potential energy. So it's all about where you define the 0 point. And so on Earth, typically we define the 0 point when we're talking about classical mechanics as the ground, but it's you can define it with respect to anything that you want.
Is this related to different levels of absolute vacuum?
Okay, so I can't really answer that question. I don't know the details. So there's ways of calculating the vacuum energy density that have. I'm just not going to go there at all. I don't know things about it. Maybe you can ask the theorists in 2 weeks. But there are ways which you can calculate the vacuum energy density, and I'm just not going to go there. Confuse everybody. All right, so yeah, sorry about that point of confusion. And this is really something you learn in freshman physics, and I should not have confused myself on that point. And then the other question that I didn't answer last week was how we knew that there were 8 gluons, 8 indistinguishable gluons, and I said there was an experiment that showed us that, but I couldn't remember exactly what the experiment was. So the experiment that you run is that you collide electrons, 2 electrons, and you make new particles. And you count if those new particles are muons or if they're quarks. And when you look at the number of events that you get that go to muons versus the number of events you get when you go to quarks, you find that there's factor 3 more quarks than what you expected. And the reason is that quarks have 3 colors. Okay? So this is when we talked about the color force last week. That's what it is. So you measure this 3. And this 3 means that the quarks have 3 colors, and then if quarks have 3 colors, then there are 8 gluons. You're not directly measuring 8 different types of gluons. We have no way of distinguishing the different types of gluons from each other. But by measuring this factor of 3, you know that the only way that happens is if there are 8 gluons. So perhaps not the most satisfying answer, but that is how we've experimentally determined that. All right, so moving on. We're going to talk now about accelerators. And let's start at the basics. So an accelerator, what is it? It's a device which increases the energy of a particle by increasing its speed. Actually, if you Google accelerators right now, I did a lot, I do a lot of Googling to find images. And the problem is you just Google accelerator, now you see a lot, all you get are like startup accelerators. So startups have this concept of taking startups and putting them in an accelerator, which then makes them go to market faster. So it's a similar idea, but in this case we're just doing the particles. So what do we accelerate? So accelerators are used to accelerate electrons, protons, and ions. So these are all charged particles, and I'll explain why later. And they're used in a really wide variety of applications, such as cancer therapy. A lot of the semiconductor devices that you use accelerators to implant ions in the material that they use for the electronics. Shrink wrap, so if you buy something in a store that has been wrapped in plastic, like if you're buying a turkey for Thanksgiving or something, those plastics have been treated with accelerators, which takes the polymers in the plastic and binds adjacent polymers together by basically bombarding the links and the bonds in the polymers with electrons, and then they form new bonds with polymers next to them. It's used heavily in biology, chemistry, and material science research. So Argonne National Lab has an accelerator, which is not used to do particle physics, but it's used to look at properties of protons properties of proteins, and a lot of other properties of materials. And then, of course, my favorite, and the one that we're talking about today, is so-called frontier physics. And this is a picture of the LHC. This is a guy driving around in it. They also ride bikes in it. There's a really nice picture of a guy on a scooter next to a bike that I like. But anyway, this is the one I picked. So you can see this is the LHC accelerator. And if you want to know more, accelerators really are ubiquitous at this point. This is a nice report that talks about everywhere that accelerators are used. All right, so how does acceleration happen? So we go back to that freshman physics that I made a mistake on last time. If you accelerate an object, you need to exert a force on it. So that's our F equals the mass times the acceleration. So this time we're interested in acceleration, so that means we need to apply force. And if you remember the forces that we talked about last time, so we know that gravity is super weak, so it's out. We know that the weak force and the strong force is short range, so we're not going to use to accelerate anything. So the only thing we have left is the electromagnetic force. And since the electromagnetic force acts on electric charge, then we can only accelerate charged particles. So that's what we're going to do. We're going to use electromagnetic forces to accelerate particles. So we can use electric fields, which push particles in the direction of the field. So if you had a constant electric field, so F is equal to E, then you would get a constant acceleration. And but since it's really hard to maintain a large constant field, so if I want to accelerate a particle a lot, I need to apply a large field to it, and that's really hard to do. So what we do instead is use alternating fields, so fields which oscillate at field strength like a sine wave. Any questions so far? So I'm going to explain how that works, how we use electromagnetic waves to accelerate particles. So this plot shows, on the y-axis, it shows the electric field strength. Okay, this is not an exact plot, though, actually, so just kind of ignore it. And this plot basically shows this shows where an electron is. So this we can have this be position. This is position. And so you can see that at this point here, there's no electric field. At this point here, a particle is getting pushed by a lot of electric field. This particle here is not getting pushed by very much, and this particle here is getting pushed in the middle. So what we do is we accelerate particles by putting an electric field on them like this. And what you can see is that this particle is only going to get accelerated a little bit, this particle is going to get accelerated medium, and this is going to be a lot. So at the end, they're all going to have kind of the same position, and if we assume that they had some initial acceleration to get to this point, they're all going to have the same acceleration. So what this looks like is, so here we have the particle just sitting there, then this is the electric field moving through, it's pushing them, and then they're all kind of in the same place, and now if I hit them with another magnetic field, or electric field, sorry, they would all be in the same place, and they would all experience the same amount of electric field. So we do this to accelerate a lot of particles at once. The fact that it's in a sine wave means that even if the particles aren't in exactly the right place, they'll end up in the right place because they've been given different amounts of acceleration, or different amounts of field. Does that make sense? Let's play it again. So the wave comes in, this guy starts getting kicked a lot, that one gets kicked medium, and then the wave passes and they're kind of all at the same spot. Does that make sense? Alright, so that's the basic principle in modern accelerators of how we accelerate things. We apply these electromagnetic fields. So this is what we call, we can do this in a linear accelerator. So this is what a linear accelerator looks like. Here it's accelerating ions. And so you have these drift tubes here, and then these gaps where you apply the electromagnetic field. So ion comes out, it drifts through here, you give it that kick, and then you turn it off, and it's got higher amount of energy, so it keeps on drifting. It gets this point, you turn on the field again, you let it drift, it has higher acceleration, so it drifts more, and so on. So these drift regions keep getting longer and longer because you're applying this electric field with the same frequency. So if I'm going to basically kick it, at like the clock, like every every 1/60th of a second, then I need this drift region to increase because their velocity is increasing. Does that make sense? All right, but there's some trouble with linear accelerators. So to achieve these very high energies, linear accelerators need to be very, very long. You can imagine that if I'm going to start a particle off from rest and then I'm going to accelerate it to something that's very fast, these tubes keep getting progressively longer, and you start needing to build something that's too long. This is the world's longest accelerator. It's at Stanford. Now it's called the SLAC National Accelerator Laboratory, but what this stands for is Stanford Linear Accelerator. And this is about 2 miles long. This is pretty impressive. Also impressive to build this in California where there's like seismic activities that go on, but they're able to control that. So this is the world's biggest accelerator. We might build another one. There might be a bigger one that's going to be built in Japan specifically to look for the Higgs, which I'll talk about later. But this right now is the world's longest one. And so basically this accelerator went to the center of mass energy of the Z boson. So that's basically as high as any linear accelerator got. And so we need to go to a circular design to make more compact machines. So if you could bend that accelerator in on itself, then you could have something that is much more compact. And then you could potentially also recycle particles. So the other problem with these is that you just get one shot. The electron goes in, it goes all the way through. There's no way you're getting it at the end again. But if you put in a circular machine, you could continually circulate those particles. And that's what the alternative to these linear accelerators is. But in order to do that, you have to be able to bend particles. So electric fields only push particles in the direction of the field. And so in order to bend them, you need magnetic fields. And so the thing about the magnetic fields is it's very different from electric fields. So electric fields, I push on something, it goes in the direction that I pushed it. In a magnetic field, I push on something, it goes in the opposite direction. Or it goes perpendicular, which is very strange. So that's the principle of electric fields or magnetic fields, and I think, yeah. So this shows a particle Here, the magnetic field is going in the direction of the x's, so it's going perpendicular to the screen. If we play it, you can see, oh, it's very short, the particle just travels in a circle. And that's how we control these particles. How we're able to bend them in a circle is by applying magnetic fields. And in a constant magnetic field, they go in the circular orbit. If you do a different field configuration, you can have particles have different trajectories. But for bending, what we care about is this constant magnetic field. Any questions on that? All right. So I want to talk a little bit about the first circular accelerator. This is the cyclotron. It was developed and designed by Ernst Lawrence for as the first combined electric and magnetic fields to produce this circular accelerator. For this, he won the Nobel Prize in 1939. And so the idea here is you've got two big magnets here, which are producing your constant magnetic field. And you put some particles, there's another step to this. Then you have this gap here, this gap between the two magnets. And in this gap, you apply that electromagnetic field. So just like you applied the gap, applied here in these gaps, an electric field. Here, in this case, you're applying that electromagnetic wave here. And so what you do is you take this low energy particle, you put it in this, and it's got some velocity. So it's going to start bending. And then when it gets to this point, you give it a kick with that electric field, and all of a sudden, it's going faster, but it's still, when it gets to this magnetic field, it has a larger radius, and then it gets kicked, then you get a larger radius, and kicks, and you get a larger radius. So each time it circles here, it gets kicked, and then it gets, its velocity increases, and then at some point you can extract it and then have a high energy beam of photons. So this is a very compact way of taking a very low energy beam and making it into a high energy beam. And so here, this is a side-on view. So these lines show the electric field. These show the magnetic field, and that's basically, that's how the device works. So this is a really revolutionary idea, hence why I got the Nobel Prize. And it really basically started the modern era of particle physics, building colliders and then just taking particles, smashing them into things, and figuring out what happens. Any questions about this?
It's also not studying E-fields, so it's not an on-off thing, it's that wave you're talking about, so it's...
Yeah. It's definitely discontinuous. But it's at the same frequency, it's at a fixed frequency. So that's one of the nice things is that this frequency of how fast it will, the frequency of basically if I was sitting here when I would see the particle is independent of the particle's velocity because the radius keeps getting bigger. So basically, it keeps traveling a bigger and bigger path each time I kick it, so I can kick it at the same time. And the idea of this kicking is kind of like if I'm pushing somebody on a swing, you know that if you push them right at the right time, you can give them, they go higher. For lack of a more elegant way to say it. It's a very similar idea, basically. I'm trying to kick this electron right when it's at the highest point so that I get the most bang for the buck out of that kick. Yeah?
Doesn't the magnetic field that bends the path rob the particle of energy, and doesn't it produce radiation?
So it does produce radiation. So yeah, I mean in the sense, okay, so yeah, so a particle that is bending will radiate photons. A charged particle that is bending will radiate photons. And so but that only happens once the particle gets to pretty high momentum, which I'll talk about the difference between the importance of momentum in a few minutes. So yes, if this were a really, really high energy electron, for example, it would be radiating photons and losing energy. But this is a low enough, what I'm talking about here is low enough energy such that radiation is not a problem. But we do not build really large circular accelerators with electrons, well, I mean, we don't do it very often. The whole reason is because they lose so much energy to this radiation of photons. Yeah, but this energy is not. This device, I've seen it. It's like the size of the palm of your hand. It's a really pretty thing, and it really just fits in the palm of your hand. And now you need a 17-mile range to make high-energy particles. But at some point, we could do this in one little room. There was actually an accelerator here, and I think it was of this old style. They made these really big. So these got to be really, really big. These magnets. They made them about the size of a large room, and they would use iron from battleships and things like that to make the magnets. But clearly, you can't make these really, really big. Yeah?
Does it make any difference what kind of a spin you have on that?
Yes, it does. It does matter what spin is on this particle, basically how it'll interact with this magnetic field. But typically we talk about all of the particles that we talk about, or at least that high-energy physicists talk about, are spin 1/2. So the spin is the same. So we assume that this particle has a spin 1/2. I think perhaps in ions you can have extra factors which change this, for example, the radius to the magnetic field relation based on the spin. But we always use spin 1/2.
Is that starting in the middle and going around to the right?
Yeah, so it goes like this. Any more questions? One second. Yeah, so this is a really revolutionary idea, but clearly you can only build these big these magnets so big. Oh, sorry, I wanted to show you a little animation of this. So this is basically what happens. You can start this over. So you have a particle that starts in the middle, and here it's getting, this is no field, and then these charges are moving away from each other. And that's basically how it's green, and then you inject it, and then you do your favorite particles. Right, so as I said, you can't make these, what they're called Ds, like the letter, because they look like the D, and that's what they call them. You can't make the Ds too big, and so what modern accelerators do is we put particles in a big tube. So the picture you've seen of the LHC is all has these tubes. And so what they do is they have a constant magnetic field in each one of these tubes, but then rather than having the particles trajectory, in the other case works because the particles trajectory changed with, and the magnetic field was big enough just to cover that entire region of how much further, how big the particle's trajectory would change. In this case, what we do is we change the magnet field strength synchronous with the particle. So as the particle is gaining energy, we're increasing the magnetic field strength so that we have a constant bending. So there's constant bending the whole time. So you can imagine, I think probably my pictures don't really help so much, but this radius of curvature depends upon the magnetic field strength. So if I wanted to keep this going in a tight little circle, what I'd have to do is continually make this magnet stronger and stronger and stronger each time that it goes around. And that is what we're doing in modern magnets. So what we have is we have little straight sections, which are our acceleration region, where we give it that little kick, just like in the case of these straight sections are the analog to this gap here. And then we have these curved regions, in which we put what are called electromagnets, since the magnetic field is generated by an electric current, and we can change the electric current to change the magnetic field strength, and that's what goes in these curved sections. Then we have straight sections because it's kind of hard to continually bend the particle. So we just do as much bending as we need. So we want to keep the bending relatively. You can imagine making this a big square and just having little curved sections on the end, but then you're making the particle bend a lot, so we get this radiation problem because they're bending a lot, so they're radiating a lot. So we try to have a balance between the number of magnets that we need and how much bending we have to apply to them. So this is basically the prototype of, or it's kind of like the canonical modern circular accelerator. This just shows a cross-section of this where you would have a vacuum tube, which is where the particles are, and then this just shows the magnets. Any questions on this? And this is how the LHC operates. And we'll go through that in more detail. All right, so it's kind of obvious why we use accelerators, but I feel like we should go through it a little bit in detail. So why would you want to accelerate particles? And in this case, I'm limiting myself to the discussion of fundamental physics. There's many reasons to use them for medical applications and other science, but I'm talking about particle physics. Okay, so the really obvious answer is to make high energy particles. That's what we've been talking about for the last half an hour. But why do we want high energy particles? And it comes back to this E equals mc squared equation, very famous equation. And what this means is that, of course, energy is equal to mass. So we know that if we have a lot of energy, we can make something with a big mass. And actually, if you look at this, what the real equation is that the energy squared is equal to m squared, c to the fourth, c is the speed of light, plus p squared. P here is the momentum of a particle. So when we talk about E equals mc squared, we see p equals 0, and 0 momentum means a particle is not moving. So in the case where a particle is not moving, then E equals mc squared. But this means that we can take a particle with small mass, like a proton, give it a lot of momentum, and then we'll have a lot of energy with which we can make new particles. So that's the whole equation that we're balancing. We're basically playing around with this equation. Yeah, so that's just what he said. Particles, momentum can be converted to mass. And the most dramatic and beautiful example of this fact, that a particle's momentum can be converted into mass, is this here. And what this is a bubble chamber picture. So back in the 60s, when particle physics was really just getting started, they had these wonderful devices called bubble chambers, which were basically typically a gas that was at a state where it had such high pressure that if a particle went through it, it would condense the gas into little liquid droplets. And so what you see here is nothing, and then you see these little droplets of liquid. Or it sometimes went the other way too. I think it was a liquid and then it can make little gas bubbles. But at any rate, something that's right on the transition between a liquid and a gas state. They were built in different ways. And so here you see nothing, and then all of a sudden you see these spirals, which are particle tracks. One of these is an electron, and the other one is a positron. You see nothing coming in here. And what this was is they had shot a beam of gamma rays, so photons. We know that photons have no mass, but they have a momentum. And that momentum here was converted into the mass of these two electrons. And so that's really, I think, the most dramatic example of the fact that you can convert momentum into mass. Here's another picture that's a little less clean. So this is from KEK, which is an accelerator in Japan. And here you see, so they had a beam of photons coming in here, and so you see one electron pair here, here's another one going off here. In some cases, you get little, just single spirals, which is where a photon knocked an electron out of an atom and it spiraled in. But this is just really gorgeous way of visualizing exactly what the particles were doing at the time. So any more questions? Yeah?
Are the photons actually hitting something?
In this case, no. So they typically are, though, in the electric field of an atom. And so they can exchange momentum with the atom, which allows this whole system to have conservation of momentum. But it's not knocking anything. It's really just the photon itself converting into an electron and a positron. Mm-hmm.
Can you go back to the equation?
Mm-hmm. Oh, sorry.
So applying that equation to a photon, the m squared is 0, so that part of it is no contribution.
Right.
Okay. So then the second term, e squared. So in classical physics, if momentum is mass times acceleration, do you need a different concept of momentum for the photon?
Yeah, so for the photon, you typically actually define the momentum in terms of the energy of the photon. If we're going to keep in this formalism. But yeah, you do need, so a momentum, in quantum mechanics or quantum field theory, momentum has a different concept. It's a property of a particle.
So basically, you're building a pyramid of concepts. You start from classical physics, mass times acceleration, you're getting, and then somewhere along the way, you're getting the energy of a photon, and you're kind of trying to convert that back into a concept.
Well, so not really. I mean, so this is true within special relativity, which is a separate idea from classical physics. And you can, in certain regimes, take special relativity, and it basically reduces down to classical physics, but there are fundamental concepts in special relativity that don't exist in classical mechanics. But, so yeah, so photons, I mean, we can measure, there's a whole thing called photon pressure. So there's like a solar wind. And so photons really do have momentum. Photons can transfer momentum to something else. And that's some of these ideas for these space explorers that go really far out in space, is that they have these big foils where all that's pushing them, essentially, is photons hitting exchanging momentum with a big sail, a solar sail. It's pretty cool idea. All right. So relativity. Okay, so this is kind of what I'm talking about, which is this where classical mechanics and special relativity diverge. So the closer that a particle gets to the speed of light, its total energy dramatically increases. So this is the particle's velocity in fractions of the speed of light. So this is 20% of the speed of light, 40, 60, 80, and then the speed of light. And this is the energy. So this is this mc squared. So when the particle has no momentum, it's just E equals mc squared, and it's here. This pink line shows you how much the total energy changes if its energy was just plus classical momentum. So plus that mv that we were talking about that's classical. If you got to the speed of light, you'd get up to here. So you'd only get a small increase in the total energy. But that's wrong. That's not what happens. In relativistic energy, as you approach the speed of light for a particle with mass, the energy goes infinite. So you can never get to the speed of light, and my total energy of the system increases a lot. And what that means is that when we're really close to the speed of light, like we are at the LHC, just increasing the energy or the velocity of the particles by a little bit dramatically increases the total energy of the system. And so that's why we say we're going from 0.9999999, last year to in 2 years we go to 0.9999999. An extra, 0.00095 says a whole lot in the terms. It actually doubles the total energy available in a collision. So that's kind of neat. And this really does show you that once you get up near the speed of light, everything you know about classical physics, you have to throw out of the window. And there's I thought this is a pretty nice, if you go to this link, it's a pretty nice discussion of this fact and of special relativity. So, yeah. All right, so the bottom line here, we accelerate particles to give them more energy, then we can create new particles like Higgs. And I want to show you this. So there was that beautiful, this has been the background of the slides the whole time. There was that beautiful bubble chamber picture of the photon converting to an electron and positron. This is kind of our modern day analog. This is a simulated Higgs event decaying to 2 photons, and so next we'll start looking at these things next week, and we'll kind of look at what modern day, sorry, this thing is dying, grab another one, what modern day bubble chamber pictures kind of look like. So, any questions so far? Okay, we've got 10 minutes left in the hour, so I'm going to hurry up. Okay, so LHC overview. Right, so we mentioned this before. It's located near Geneva, Switzerland. This is the Swiss-French countryside. Here's the Atlas experiment. I lived right there. When I was there, and you could walk across, the tunnel was 100 meters on the ground, so you couldn't see it, but, that's kind of fun to be able to know that you're walking. There's an accelerator under your street in your quiet little French town. So here it is. This tunnel ranges from 50 meters under the earth to 150 meters under the earth, about an average of 100 meters. And it goes under the Jura Mountains, and you have the 4 collision halls. This Atlas experiment, which I'll talk about a lot. CMS experiment, our cross-town wrangles, cross-ring wrangles. Then ALICE if you're in the US, or ALICE if you're in France, Europe, experiment, and LHCb, which are 2 other experiments which I will not talk much about at all. And this tunnel is 27 kilometers long, and a center of energy below the Earth, and 5 protons at a center of mass energy of 14 TeV. That's 14,000 times the rest mass energy of the proton. Let's look at some of the technical specs. So this ring has 9,600 magnets. So there's bending magnets, so those magnets that do the bending that I was talking about. There are 1,200 of those. They're dipoles, and these actually are most of the total magnet mass. I'll talk about these dipoles in a minute. They're really important. The rest of all those other magnets range from big to small, and what they do is they focus and correct the beam. So you imagine that you've got a bunch of particles circulating in the accelerator. You're bending them, you're accelerating them, you're bending them, you're accelerating them. And what you need to do is sometimes they start to stray. And if you imagine if they start to stray and then you keep accelerating them, you're going to make them go even further astray. So we use these other magnets to focus the beams, to kind of catch the ones that are going in the wrong direction, make them, and then make them go in the right direction. So there's a lot of magnets that do that. That's where all this extra, all the big difference in these 2 numbers come from. But these dipoles really are the workhorse of the LHC.
Are the focusing magnets ad hoc, or are they just permanently positioned?
They're permanently positioned. You can change their energy slightly, so you can change the magnetic field slightly by changing the current in them. And there's, so there's lots of very detailed calculations that go into exactly what types of magnets where, because you can never perfectly correct this, so that they're constantly fine-tuning that, actually. They're also changing the beam energy itself constantly to try to find this point where you get the least amount of that particles going astray.
Well, then they're watching the particles.
Yeah, that could be a whole talk. It's really interesting. I don't do anything that is like that, but I've gone to talks about that, and it's a very interesting field. Oh, right, and these are cooled to 1.7 degrees above absolute zero. So that's colder than outer space for all these magnets. There's 8 of those cavities that do the acceleration per beam. So there's 2 beams, counter-rotating beams, and each one gets that kick 8 times every time that it comes around. And that kick is delivering is 2 million volts at 400 megahertz. And for contrast, your wall plug, which is what I'm getting at here, is 120 volts at 60 hertz. That's a whole lot of power. And it's basically, to power the LHC, it's like the size of a French city, small city, I guess. And it's shut down over winter because electricity costs are too high. So in Europe, everybody uses heating in the winter, not surprising, Switzerland, it's mountains. And so electricity is too expensive, so that's when they shut it down. And Fermilab, which is the accelerator that shut down recently, would shut down in the summer, and that's because in the US, we spend a lot more energy on air conditioning. And so you can't run the accelerator in the summer when air conditioning is driving up the cost of energy. And this is all in a vacuum system. Sorry. And so the beam vacuum, so the place where the particles are going, is 10 to the minus 13 of the Earth's atmosphere. It's really, really pure vacuum. That's why it's very thin air. So this isn't completely pure. So that's why we're saying we're creating particles out of very, very thin air. 10 to the minus 13 times. So I want to spend another minute talking about these dipoles. So each one of these dipoles is 35 tons. They're 14.3 meters long, and they provide a field of 8.3 Tesla. So what does that mean? So the Earth's magnetic field is 5 times 10 to the minus 5 Tesla, much, much smaller. Refrigerator magnet, which is the magnet that we're all most familiar with, is 10 to the minus 3 Tesla. So this is 1,000 times, this is almost 10,000 times bigger. But this is not actually, without this, out of the scope of stuff that we interact with. Who's had an MRI? I've had a bunch of them actually, right? So you go and sit in that big magnet, and those are about 1.5 to 3 Tesla. So if you've ever had to have like a high resolution MRI, you're going to a 3 Tesla machine. 1.5 is kind of the standard one. So I wanted to show you this is getting pretty technical, but I wanted to show you what the magnetic field in these LHC dipoles looks like. So this is one beam, and this is the other beam. So one beam goes in that way, the other beam comes out this way, and this is the Pikes, and these are the wires that make the magnetic field. And these lines show the direction of the magnetic field. And if I remember, I told you that constant magnetic fields cause particles to bend. Well, you can see that the magnetic field in the middle of his pipe is constant. So that's kind of cool. It's just showing we're making that constant field that we had in those big D magnets now in small little volumes for the pipe. And if I were to change the current in these wires, this field strength with these arrows would get fatter or thinner. Neat. This is just what it looks like in detail. These are the two beam pipes. And then you have inside, this is all a big cryostat volume. So this whole thing needs to be kept really, really cold because, well, I'll talk about why in a minute. But yeah, this is what it looks like. Here are the details. All right, so, yeah, you have a question?
Are both beams traveling in the same pipe?
There's two separate pipes.
Or separate?
And then near the collision points, they get put into the same pipe. Okay, I'm not going to actually talk about this. So basically, you have to get them really, really cold so that you can put really high currents inside of the magnets, which makes high fields. Yeah, it's because of, you use superconductivity. I don't really have time to go over it. We can talk about it later if you guys want to, but since it's not particle physics, I'm going to skip it for now. But I do want to talk about the accident. Very famous. I don't know if you remember, but in 2008, the LHC was all ready to turn on, and I was at my husband's aunt's house. We were there with a bunch of family for a weekend, and his cousin's husband said, "Oh, I heard there was like a problem in the LHC. There had been problems in the LHC before." And I was like, "Oh, it was probably just like a little magnet problem," because I heard it was a magnet problem. It's like, "Oh, it was probably just a little magnet problem. This kind of standard might delay us by a week." Then I get back from this weekend on Monday, and word starts to leak out as to what happened. What they first started calling was that they said, "Oh, we had a helium leak." And so what that helium leak, there's a euphemism or something, an understatement. What happened was that, so these magnets are cooled by superfluid helium. So this is taking helium, cooling it down to 1.7 Kelvin, and when it's superfluid, it's really dense. And basically, one of these magnets went from superconducting, which means there's no resistance when current is passing through it, to resistive. It heated up. And what happens is all of a sudden, all that current that was traveling with no resistance, all of a sudden feels resistance. So it starts dumping all of its energy into the magnet. And so this one little section of a magnet got really, really hot, enough so that it started boiling the superfluid helium. And when superfluid helium goes from a liquid to a gas state, it expands. And it expands a whole lot. And what it did was it ripped these 35-ton magnets off of their stands. So these things are anchored into the concrete. They were ripped out of the stands. They took these big magnets and basically ripped them apart. And this is all from superfluid helium going from its superfluid state to gas. And it damaged 50 magnets. 50 magnets bad enough that we had to take them up to the surface and repair them. There were a number of other ones that had to have other repairs inside of the tunnel. And actually, these are nice pictures that were cleaned up, but the first pictures that came out of it, the whole thing was covered in ice because everything in the air condensed. This is still really cold helium that got out. So anyways, it was a huge fiasco. And it delayed the start of the experiment until very late 2009. In fact, we didn't reach high energy collisions until 2010. But we were extremely happy when it happened. This is the Atlas control room. I was upstairs not this night. I wasn't there for September 2009, so that was the lower energy collisions. We did the same thing. Everybody got really excited in March the next year when we all had collisions. But yeah, so people were really happy. This extremely enthusiastic woman was a staff scientist in my group, and she had worked a really, really, really long time on making one of the detectors work. So, and she's also a very demonstrative person in this way, so I just love showing this picture and her excitement.
Can you tell us a little bit more about the reason that
Yeah.
the accident happened? What caused the magnet
The
to...
quench, yeah, it's what's called quenching when it goes from superconducting to not superconducting. So this is a normal thing that happens. Magnets go from superconducting to not superconducting for a variety of reasons. So it could be that some particles got out of the test beam and implanted a little heat into the superconducting wire. Could have been a defect in the superconducting wire. Those happen. That's fine. This is expected. The LHC is expected to have a number of these so-called quenches a year. But we know how to deal with them, typically. We're supposed to be able to deal with them. So what happens is there's monitors that monitor the the resistance in the magnet. And if it sees it start to increase, all of a sudden it says, oh crap, there's a quench happening. I'm going to heat up an entire long section of magnets. So what it does is the system that starts heating up all these magnets and makes a bunch of them go non-superconducting at the same time. And why this is good is because then rather than dumping all of that resistance into one little tiny point, you're distributing it along, you're distributing it along the whole long line of magnets. And so that system's supposed to work, but it failed in this case. It did not detect that this was happening, and so all of that energy went into that very small space, and hence the big explosion. So right now, they're putting in new fixes for that. They're taking magnets out and fixing them and putting in these detection systems that will save it. There was a little bit more to it. There was some mechanical, in the particular place where it happens, there was a mechanical defect that they now know is in several places in the ring and they're fixing now. So it was more than just a normal. It was basically this thing you expect to happen, but not in the place that it did, which is why the protection systems weren't there. But yeah.
But I heard that the reason was insufficient testing due to the political pressure to open the accelerator
I don't know. I'm not going to comment on that. I know some Fermilab magnet people, and of course, Fermilab side is all, well, certain being really cocky and they think they know what they're doing and whatever. They really don't. They've never run a superconducting machine before. But I don't know. Yeah. There was a lot of pressure. And actually, the experiments weren't ready. We weren't really ready. If we had started up then, we wouldn't have gotten the Higgs results out as quickly. That extra year gave us a lot of time to fix and understand a lot of things. So, in the end, I don't think it delayed that whole procedure very much. Okay, so the last thing I want to say is basically just that, so the LHC starts from a bottle of protons, which is a hydrogen bottle. This is actually it, or one of them. I'm losing these. And then it goes through the LHC is the fifth in the stage of accelerators. So there's a little linear accelerator, and then 2 or 3 smaller circular accelerators, and then finally the LHC. And it's taking, basically going up to 7,000 times the rest energy of the proton. We do this with 3,000 bunches of protons, and there's 10 to 11 of them in each bunch. And I'm just going to show you a little video of what this looks like. So that was a proton going through the accelerator. It's going into the first booster, which bumps it up to 1.4 GeV. It goes to this other accelerator, the PS, and it goes into the SPS, supertron here, and then they go into the LHC. So it's showing them the beams crossing. We're going to go inside the tunnel, physics graffiti on the wall. We're passing the French-Swiss border. This is our cartoon proton with 3 quarks inside of different colors. And now we're going to the Atlas Collision Hall. And so this is taking us inside the Atlas detector. The protons are colliding, they're creating a bunch of new particles, and we're seeing a bunch of energy detector. So what we'll start talking about next week is basically what all this is. So first, how collisions produce new particles, and then how we see them in the detector. And I think this is a Higgs boson also that we have there. So that's it. All right, so we'll